Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll conclude Chapter 3 on two-sample inference. So we've scrolled down to the two-sample inference, and we'll open this up. And of course, you are, I hope, running this R code along with me for each of these examples. In the first third of this chapter, we looked at visualizing data from independent samples. In the second video, we looked at using the two-sample t-test to make comparisons between means for independent samples. In this section, we're looking at when your data are dependent, when you have paired data, but still comparing whether the means are different between our samples. So we're still interested in whether the mean for the first sample, or rather for the first population, is different from the second population. We're going to learn about the differences in the population means based on samples from those two populations. But now we have paired data. So by taking differences within pairs, two dependent samples are transformed into a single sample, which contains the relevant information for inferences of whether the difference, mu d, say is different from 0, for example. All right, so let's, in our previous examples, we had a couple examples of paired data. One was for water well data, and for example, say you went to a water well and measured a certain compound in that well, and then you went back a month later and measured from the same well, the same compound, and you wanted to know how that value differed over time. So you could calculate the first one minus the second one, or vice versa, and call that D for the difference. And for all the observations, we now have a bunch of differences. So we now have reduced the two samples into a single sample of differences. So I hope that makes sense, that we now have just a single column, and our response variable now is the difference between the two paired values. What does that mean? It means we can go back a chapter and perform a one sample inference on the differences. All right, so I'm just scrolling through. All of this is one sample t-test stuff where we've got the mean, which is now the mean of the differences, minus 0, is divided by the standard error is our t-statistic, and we do plain old one sample t-test stuff for that. So I'm going to show you a few ways to visualize paired data as well as perform the inference for paired data. So the most natural way to enter paired data is just simply as two columns in your data frame. First column for the first measurement, second column for the second measurement, and that structure actually makes it very easy to create a third column, which is the differences. All right, so let's take a look at an example where we're testing the IQ, the intelligent quotient, for identical twins who, if you can believe it or not, were raised apart. One of the twins was raised by their genetic parents, and the other went to foster parents. Now, I actually don't recall the data story for this, but there must have been a really serious issue to separate twins to raise one with foster parents, and have one of the twins also raised by the genetic parents. Sometimes there are, tragedies around the world that provide a natural experiment that would be sort of unethical to do, as a psychologist who'd want to study this. But sometimes tragedy leads us to an experimental condition that we can never do in the lab. So here we're going to call mu f the mean IQ for twins that are raised by their foster parents, okay? And mu g is the population mean IQ for the twin that's raised by their genetic parents. And we want to compare basically mu f minus mu g, the difference between these, to see whether you have higher IQ if you're raised by your genetic parents or by foster parents, or does it matter? Twins are, of course, especially identical twins are the ideal situation for assessing and you're all screaming the phrase at me as I'm sitting here trying to come up with it. Nature versus nurture, right? So nature is the DNA that these twins have. If they're identical, they start from the same egg and sperm and split, and they have exactly the same genetic code and go on. And so now and I just said it, it's hard to make these videos, man. All right. Well, the thing I said before. So it's not the genetics, but it's the way you were raised. All right. That's what we're comparing. All right. Here we go. So we're gonna. Oh, okay. This is old stuff. So we're gonna create foster IQs and genetic IQs, and of course the sample sizes between these two groups are the same. And we're going to create a third variable called diff, which is the difference between them. We're setting the axes limits as the difference, or the range of all those values. And I'm making a single data frame called IQ, which has 3 columns: the foster, the genetic, and the differences, all in one data frame. So if you're running the code, you can type IQ after you've run this, and you'll see those 3 separate columns. Finally, I'm going to create a plot, and the plot's going to look like this. Okay, let me zoom out just a tiny bit. There's a lot going on in this plot. I've mapped the foster IQ to the horizontal axis, the genetic IQ to the vertical axis, and each point represents one of the twin pairs. Okay, and I have a square axis here. Notice that it goes from 60 to about 140 on each x and y, and it's square so that the proportions are the same. So I now have this diagonal 45-degree line, and this is a reference line just to point out that if the IQ scores are the same between foster and genetically raised twins, then we should expect the points to fall along this line. And for the most part, they do. So far we have evidence that where you're raised doesn't matter that much as your genetics for IQ. So let's scroll up and take a look at what we did in ggplot to make that work. There's a lot of lines here, but they're all pretty straightforward. So we're going to run ggplot, and IQ is the data frame. We're assigning the foster IQ to the x variable and the genetic IQ to the y variable, to the y-axis. And where I would start, if when I was creating this plot was, I went through several revisions before I got this plot. The first step is I would just create points and then print the plot. And then I would look at the points and say, okay, what else do I need? I added a rug, which are, if I page down for a second, the tick marks along the axes. And in a way that sort of shows roughly what the distributions are for each variable independent of the other. I'll page back up. Then I decided, let me add a reference line to this. And so there's the geometric object AB line. The A and the B refer to the intercept and the slope. So I have a 0 intercept and a slope of 1. That gives us a diagonal line. And alpha equals 0.2 says it's going to be fairly light. And notice I make that the first object that I plot, so that the points, the actual data, lie on top of the line. If we page down for a second, it only happens a couple times, but some of my points lie right on top of the line. That's when the IQs were identical, or at least for that measurement, for the genetic and the foster kids. And then I realized, well, it's to make a fair visual comparison, I really need my axes to be square so that the diagonal line is actually 45 degrees and it's not shallow if I had like a 4:6 photograph aspect ratio, for example. So the chord equal is what sets equal coordinate tick marks, so that every inch was like 20 points of IQ, for example. And then finally, the x and the y limits are going to be the axis limits that I got from this command here. So I have the same minimum and maximum based on all the observations for both axes. And finally, I label my plot's title. So a lot of individual steps. It will take you 5 or 10 or 20 minutes to make a plot like this the first time. Actually, it would take you less because you just copy my code. But the point is that plotting is something that is iterative, just like writing. So we're doing visual communication, just like you do written communication if you're writing and you want to revise until you have a nice, easy to understand plot. So one thing that we see is that these points are basically on the line. If we were to see a lot of these points, say, above the line, that would indicate that the genetic IQ was higher than the foster IQ. But we're not seeing that right now. All right, let's scroll down. And so the actual comparison we're making is going to be on the difference of IQs. So I'm going to make a little histogram of that. And we've seen plots like this back in chapter 0. I've added a vertical red dashed line at 0, which is the null hypothesis. And one thing we see is that these data distributions are basically centered on 0. There's 3 plots of the same information. The top one is a histogram with the density curve on top. The middle one is a violin plot with a box plot in the center. The bottom one is just a box plot by itself. And they're all, the median actually here is equal to 0. So we're going to have not insufficient evidence to reject the null. The data are pretty much consistent with the null hypothesis here. How would we test the normality assumption? In fact, what is the assumptions for this test? Well, we have basically a one-sample test of the differences. So we need to check whether the differences in IQ are normal, and we can use the bootstrap for doing that. And so I'm going to scroll down a little bit and look at the result. On the left is for the bootstrap. On the top is the distribution of the differences, and on the bottom we have the bootstrap sampling distribution. And what do we think? This looks really good. The black and red lines match beautifully in the tails, which is the most important part. There's a little bit of difference from normality in the center, but that's not really going to affect our inference. So I feel really good about using the one sample t-test to check, to test the assumption and to construct confidence intervals. So here is our one sample t-test of the differences. We have a t statistic of 0.1, and we're looking for t statistics that are greater than about 2 or 2.2. So this is a really small t statistic. That leads us to a really large p-value. If we look at the plot from a function I made to plot the p-value from a t-test function, you can see it takes up almost the entire curve. So we have a lot of, the data are basically very consistent with the null hypothesis. A confidence interval, 95% confidence interval of the difference in the genetic versus foster IQs is basically between -3 and +3. So looks like it doesn't matter whether you are raised by foster or your genetic children. Just to show you another way to run this in R, if we had the two separate, so instead of calculating the difference, if we just have the column for genetic and the column for foster, you can specify an argument called paired equals true, which, notice these numbers are the same as what we saw above. And so it effectively in the function calculates the difference between these two columns and then does the one sample analysis. All right. All right. One more example, a paired comparison of two sleep remedies. So the background of this is we've got 10 individuals, and for each individual we know what their average amount of sleep is. For example, I care very much about sleeping very well, so I have a Fitbit, have had one since 2009, that in addition to tracking my steps during the day, tracks my sleep at night. And getting a solid 8 hours for me is just about right for me to feel like I'm a functioning human the next day. And so for these 10 individuals, we would know what their average amount of sleep was. And then we give them each two sleep remedies. One sleep remedy, which we'll call remedy A, on a particular night, and then on another night we'll give them sleep remedy B. And we'll know, so what we care about is what is the amount of sleep gained in hours from these two sleep remedies. So we effectively need to calculate the difference of how much sleep did I get on remedy A minus what my average sleep is, and then the same thing for remedy B. So I'm going to scroll down and take a look at the data first, and I'm going to skip over a lot of the code because I've described the code in the previous example. On the horizontal axis we have the additional sleep from remedy A, and on the vertical axis we have the additional sleep from remedy B. And one thing to note right away is the diagonal line, okay, and that most of the data fall above that line. Furthermore, the zero lines for both A and B is the first bright white grid line. And so for most people have gained sleep. Okay, there are some people, there are 3, maybe 4 individuals, maybe just 3, who have less sleep on remedy A along the horizontal axis. And on the vertical axis, there's only one person who has slightly less than average sleep on remedy B, but basically the same as their average amount of sleep, but everyone else had more. And you can also see that, yeah, the points are above the line, which indicate that you get more sleep on remedy B than on A. Let me scroll up to see whether we've missed anything. I've defined my notation, and I've created a data frame as well with the difference, and I'm doing B minus A. So the differences are how much more sleep do you get on remedy B than with A. So all but one of these is positive, and the 0.02 is basically 0. So it looks like B is doing much better than A in terms of giving these people more sleep. Here I'm plotting the data. We've got histogram, box plot, and stuff. What else? Okay. And I'm testing also the model assumption. So on the left, we've got the distribution of the differences, B minus A, and we see that it's greater than 0. The dashed line at 0 is giving us the reference line, but we also have a bit of right skewness. A lot of the points are centered around maybe 1.5 or 2 hours, but then we have this one extreme value out here that's causing us to see some skewness. When we look at on the right hand side, we're looking at the bootstrap sampling distribution of the differences. The top is the histogram, which is the same as the top left plot over here. And the one sample bootstrap sampling distribution of the mean is below. Now, what do we think about this plot in terms of normality? I'm going to zoom in on it a bit. You're probably thinking doesn't look great, right? Systematically, we have the distribution is less than the normal curve on the far left. On the mid left, it's greater. Mid right is lower, and on the far right, about the same, maybe slightly greater. And so this is due to the right skewness of, oops, it's the wrong way, the right skewness of our data. And effectively, this right skewness is due almost entirely to this one point out in the far right. So I feel a bit uncomfortable using a one sample t-test to analyze this data because I have this big difference from normality. Instead, what I would do is wait until we get to chapter 6 and use the Wilcoxon-Mann-Whitney test or something like that that allows us to not assume normality to compare whether this mean is different from 0 or not. All right, so I go ahead and show the result for a t-test here, but I feel a little bit uncomfortable with that, with our inference here. In this case, this is one of those cases, however, where, look at this distribution of differences. All but one point is greater than 0, and by quite a bit. And the one value that's less than 0 is basically 0. So sometimes there's so much evidence that statistics isn't really necessary to draw conclusions. That's what we do most of the time in our lives. We rarely stop to perform a hypothesis test. We just make decisions anyway. And for the most part, some things work out. So even though I feel uncomfortable about this particular p-value, I'm quite certain that the inference here would lead to the same conclusion even if we did a non-parametric test from chapter 6. All right, here's our tiny, tiny p-value, almost 4 standard deviations away out in the tail. All right, so that's paired data. The last question I have is, in what order should these remedies, that is sleep remedy A and sleep remedy B, be given to the patients? Okay, so should you give everyone remedy A and then remedy B? Or should you give everyone B and then A? Or should you give half and half? Should it be random? Should you make all of the women do A and then B, and then all the men do B then A? So these are experimental design questions that you may need to grapple with if you're in the sciences or social sciences. And the answer that is probably preferred here is that you want to randomize. In general, I have a saying that you should block what you can. We haven't discussed blocking yet. And then randomize the rest. And so these are things, for example, if you did everyone doing sleep remedy A and then sleep remedy B, the treatment that you gave was A then B. And so the effect that you're actually testing is, are the sleep remedy means different when you give someone sleep remedy A and then give them sleep remedy B. And that's not really what you want to test. You don't want to have that condition, get that conditional ordering of A then B. You really want to remove that ordering. And the way to remove that ordering, that dependency on order, is to randomize the order that you assign the treatment for each individual. So person A, do they get A first or B first? You flip a coin and then assign A first if you get heads, for example. So randomization is going to save you from biases due to poor experimental design. All right, my last comment in this chapter is, should you even be comparing means? So imagine a situation, the top situation is great because we have basically 2 identical distributions with the same variances. The only difference between these two are the location of the centers. And in this case, because that's the only real feature of difference, that's the difference that's the feature that you want to compare. On the bottom, we have a very different situation. These 2 distributions are still normal distributions, but on the left we have a very tightly, we have a distribution with small variance, okay? All the points sort of cluster very tightly around 16 or so. And on the right we have a distribution that's centered maybe around 22 or so, but it has a very wide variance. So maybe the means are not the interesting feature here. Maybe the feature of interest is the variance, or or some other feature, for example, the proportion of the distribution that's less than 15, or something like that. So I do have an example that I describe in the text above. I encourage you to read that. But the point is that there's nothing really special about the mean in terms of that being the only feature that we ever care about. Most of our methods are designed for the mean because that represents the center or the average observation. But we often, there are sometimes when you care about other quantities. And when you've got distributions that are very different, perhaps you should consider a different quantity. In fact, it's possible to see distributions that are bimodal, that have two humps, in which case, maybe you don't care about the mean at all for a distribution that has two humps. Maybe you want to worry about what makes a distribution bimodal. There's some process underlying the data that has this bifurcation, and you end up in one hump or the other. What causes that? Maybe that's the interesting thing to analyze. All right, so that concludes Chapter 3 on two-sample inference.